morning. How y'all doing? Let your culture of safety folks. Forming a line team. We're getting a little over 13,500 partners now after about 2.5 years. And Mr. Mack Turner here is Executive Director with ISPC, that's Institute for Safety in Powerline Construction. He's going to be here today. He's going to be presenting Back to Basics Electricity 101. So if you haven't seen any of Mack's shares and his presentations with Electriculture of Safety, just contact me and I'll send them to you. Just safety training at beermeters.com, and I'll send them all to you. Incident for safety and Powerline Construction. You all come out, what, Mack, 8 times? About 8 times a year?
Yeah, I think about that.
About
That's
8
what
times.
We've been this year.
Yeah.
Mm-hmm.
So ISPC is serious about safety. They're serious about sharing their expertise and their experience, their time and talent. I know Mack, he thrives and lives out of Utah. So you take, what, a day and a half, almost 2 days to get here, Mack?
Well, airplanes make it a little easier. Yeah. If I was driving, it'd be about 3 days.
Yeah, yeah. So, so Mack has an interesting story. Like to, if you could, Mack, if you could share some of that story with us as far as some of your upbringing and what you've been used to growing up and how you got into line work.
Well, I grew up in rural central Utah, and that's where I live. Very limited population, kind of out of the way, up in the mountains. So the valley floor I live in is 7,200 feet elevation and mountains around me. I grew up on a sheep and cattle ranch, so our income was mostly cattle and sheep. We also grew potatoes and had that as an income growing up, and that's what I wanted to be. So I went to college and I went into agribusiness, came out, thought that I could buy my folks out. They was ready to retire, so I tried that and slowly started starving to death. That was back in the high interest years of the early 80s, where interest was 13.6%, and I found that I couldn't hardly make the interest payment, let alone live on what the income was. So I got into the line industry, and I took a part-time job digging pole holes the first year, and then they called me back and put me on full-time. So I went through an apprenticeship, and then as I progressed from a co-op to a contractor, I started into the safety and leadership field. Still wore my hooks for a lot of years, but really went as a contractor mainly into the safety field and leadership development, stuff like that. Went to work for a large utility in Arizona, and my official title was I was over the safety department, the training department, and the standards department. Enjoyed that an awful lot, and I learned an awful lot from a lot of people. And then I left, and here I am at the Institute for Safety in Powerline Construction. We're a not-for-profit company. We're focused on electrical utility safety, and that's just that is our whole mission, is nobody's got to get hurt. And we do that in a lot of ways. We do a lot of training. We go on site and do training. We develop curriculum for people. We have curriculum that you can buy. We do a lot of auditing, a lot of writing of programs, safety manuals, work methods, stuff like that. And then unfortunately we get into litigation as well. So we're kind of a full service company, but this industry has taught me a lot, and it's given me a lot. And I'm very proud to be part of this industry. I'm proud to be one of the people who've helped keep the lights on over the years. But I'm especially proud to be where I am now, because if we don't focus on safety and not anything else, safety's got to be number one, we can't do our jobs and people get hurt. So I'm very happy to be where I am, and I'm happy to be here, and I appreciate Beer Meters for inviting us and for putting this on and for doing this service for the industry. So thank you very much.
Thank you, Mack. Yeah, I have a great privilege and an honor to be connected with ISPC and the folks at ISPC, and I follow some of their work and seen some of their products that they put out as far as work methods and some of their films they do, helping the apprentices and helping folks that have been in line work for decades. Either way, and man, it's a great honor to see what they do. You got Mr. Jimmy Vaughn, you got Mark Forster, Tony Boyd, and they just put out an amazing product, very professional. So it's definitely going to enhance what you already have established to make it even better. So definitely reach out to these folks. And Mac, thank you for everything that you guys do.
Appreciate
Thank you, brother. Okay, thank you.
Today's program is Back to Basics Electricity 101, and before we get started into it, I'd really like to talk about what we see and what I've seen in my career. When I started in this industry back in the early 80s, hurting people or even killing people wasn't as big a deal as it is now. And if you look back at the origins of safety back in the mines of the U.S., you know, they didn't think too much of safety, and when somebody died or got hurt, there was 10 people waiting outside the gate to work, so they didn't focus too much on it. But as we got smarter in our workplaces, we've decided that people are important, and we can't hurt people, and we can't kill people. And so we've progressed over the years to where we, in our workplace, and especially in this industry, we have a culture of safety. And that's a good thing, because people, us, are important. And I don't care how many robots or widgets or whatever we make, it's still going to take people that's breathing and walking and have some knowledge to keep the lights on and to do other work as well. It's really good that we do focus on safety. However, it seems like every time I look at the internet or I get a phone call or something, somebody's gotten hurt or somebody has died. And you would think with all the technology we have, with all the tools that we have, with all the focus on safety that we have, that people wouldn't still get hurt and people wouldn't die in our industry, but it keeps happening. And we as consultants to the industry, we see a lot of trends. And in previous ECOS episodes, I've talked about things like accountability and different things that we really need to focus on. But one of the things that I've noticed and we notice at our company is that we have a hard time remembering the basics of electricity and how it applies to us. Almost any job site that I go out on and I start asking questions, I will ask journeymen, tell me what Ohm's law is. And they get a blank stare. And they'll try and tell me and that, but you know, it makes me wonder, well, do we really apply simple things like Ohm's law into our everyday work practices? Do we think about those things? Do we think about how circuits work? Do we think about the devices that we have on our system to help us and protect the system and that? So I decided to put a little presentation together. I've done variations of it for years and years, really going back to the basics of electricity. And I don't want to insult anybody's intelligence, but we all have been taught how electricity works. The problem is we forget it. We forget to apply it. We think that we're better than that we know that, and we end up getting hurt, or heaven forbid that we die on the job. So that's basically what this is about. So let's start into this. So electricity is part of our lives, folks. It's a wonderful thing that we cannot do without anymore. Now, as I was growing up, I grew up without electricity in the household for the early part of my life. And then after we got electricity, if it went out for a day or so, nobody cared. It was expected, you know, things happen, weather happens. But as we get more connected in this country to electrical systems and devices and that, there is an expectation out there that the lights always turn on, that they never go out. And it's important in our lives nowadays from even a health standpoint. We rely on the electricity getting to the hospitals and to medical facilities. We depend on it to provide us oxygen sometimes, and a cool place to get away from the hot South Carolina heat, and a lot of things. So it's really important in our lives anymore. But what we need to know is that when all is right with the electricity, it's safe and reliable. Okay, it's one of those silent miracles that power our everyday lives. But when it's not right, then electricity causes many issues. If you can see it, if you can smell it, if you can taste it, if you can hear it, something's going wrong. And when the power goes out, it can cause a lot of problems. But it also can cause problems with us as workers in the field. And we as workers in the electrical field need to understand how to work with the electricity so that we can safely keep the electrons flowing, because that's what we do. Okay, and we can do that day in and day out. We can do that our whole careers and never have a problem. But the safety rules, the rules of electricity, rules of working with it, we need to follow that, because it really is a silent killer. We in our industry are very fortunate. We have training like very few other industries. I can only really think about 2 other industries that has the type and the amount of training and expectations with training that we do in the electrical field. One is airline pilots, and they have an awful lot of training. They have a lot of rules. They got procedures they have to follow each way, every time. And in the nuclear industry, the same way. Whether it's a nuclear power plant or whether it's other nuclear-related industries, there has to be a lot of training. There has to be a lot of adherence to the procedures and the rules and to safety. Other than that, I really can't think of an industry that receives more training, has better tools and equipment, has better conditions to work. And I know that this is a hazardous industry. I've seen a lot of suffering and death and burned up things in my career. But really, if we are trained well, and if we keep our retraining, because as we get older, as we progress through things and we haven't done things for a while, we tend to forget. So we need to demand that we keep our continuing education going, because we are one of the best trained workforces out there, right up with airline workers and nuclear workers. But when we forget some basic rules, some basic procedures, then incidents happen. Now, a lot of incidents happen and nobody gets hurt. But an incident is an incident. There's a cost to it. And that does affect us. So let's just relearn some basic electrical rules. And I don't want to insult anybody's intelligence. But really, we find that people kind of forgot some of these things. So, producing electricity. Electricity is produced when a force is applied to a material. A material must have 1, free electrons, and 2, the force to make electrons flow. And electrons flow in conductors. The best conductors are gold, silver, platinum, copper, aluminum, and brass. Those are really good conductors. Electricity flows with not as much resistance. And then we have insulators that are used to keep electrons from flowing. Some good insulators are porcelain, polymer, glass, rubber, and air. And we use all of these in our industry. So, how do we produce electricity? Electricity is produced, 1, by friction, creates a static charge when 2 materials are rubbed together. It is produced by heat. When heat is applied to certain combinations of metals, it causes electricity to flow. By light. When light hits certain materials such as sodium or lithium, the light energy causes electricity to flow in the other material. Magnetism. When a wire is moved quickly through a magnetic field, the electricity will begin to flow through the wire. Now, most of you know how electricity is generated in our systems, and that magnetism is a big producer of electricity in our electrical systems. Pressure, when pressure is applied to some materials like crystals, the pressure causes a flow of electricity. This is called piezoelectricity. And then chemical reaction. A combination of certain solids and liquids will produce a flow of electricity. So there's various ways to produce it. But no matter how it's produced, it'll either be direct current or alternating current. So we need to understand that there are two kinds. So AC is what we see in most of our electrical systems, in our homes, in our businesses, and all of that. So DC current, we do have DC facilities in our country. We do have some DC lines. We have lots of equipment and lots of processes that use DC electricity in our country. But one way that we all use DC electricity is in our automobiles. Okay? But we don't see it a whole lot in our electrical systems. We do see it in some areas and in some circumstances. So early on in my career, we had to replace buswork in a gold and copper refinery. And all of that buswork was DC. And I got a real wake-up call to the power of DC. We think, it's nothing. But folks, that's a whole nother skill set. Anyway, generating stations produce AC using principles of magnetism. And the other 5 methods produce DC electricity. So there are some basic units of electrical measurement. One, there is current, and then voltage. So current is a measure of electrons flowing in a circuit. It's measured in amps or amperes. Large loads result in high current flow. And it is designated with the letter I. So when we see I in an equation, we're talking about current. Now voltage is pressure or force, or the driving of the current. It is measured in volts. That's high voltage is measured in kilovolts or kVs, and it requires thick insulation and large separation for high voltages, and it's designated with a V or an E. Opposition to current, which is called, let me get through this just a little bit here and we'll discuss these. It is called resistance. So that's the opposition to the current flow. So even metals like gold have some resistance. Insulating materials have very high resistance, and it's noted with the letter R, and it's measured in ohms. Then we have power. It's a measure of energy required for work, running a motor or lights. Everything in the circuit has power or a load rating. It's designated with a P. It's measured in volt amps, and large quantities are measured in kilovolt amps or megavolt amps. And it's calculated by multiplying voltage times current. So there's some equations there. And volt amps are the result of watts, which is W, and vars of a circuit. Now down here in the bottom left corner of this slide, there's a little illustration. So when I talk about electricity to people who really don't understand it, I talk about a water hose. So in a hose of water, we have all of these things. We have current, which is the flow of the water, and how much water flows through that hose. We have the voltage, or the pressure, and how much water pressure that forces that water to flow through the hose. And then we have the resistance, the type of the hose, the size of the hose, all of that. So the resistance is trying to hold it back. The pressure is the how much pressure is behind it, or the volts, and the current is the amount of flow in that circuit. And it's a very simple thing to remember. So it boils down to Ohm's law. So Ohm's law establishes the relationship between voltage, currents, and resistance. This relationship can be expressed mathematically by the equation E equals I times R. So it's voltage equals the current times the resistance. I can go out on most job sites or most work sites and ask the crew to explain Ohm's law to me. And most of the time they can't. And that's frightening to me. Because, yeah, we all know what it is, but what correlation does it have to the work that we're doing every day? We feel like we're above that, or we're past that. And if we understand Ohm's law, we can stay safe doing that work. We can produce and make the flow of electricity happen seamlessly and effortlessly. Nobody has to get hurt. But when we don't pay attention to it, bad things can happen. So Ohm's law can be rearranged to find a missing value. It's just a simple algebraic equation. Now, I didn't have algebra in high school. I had to go to college before I got it because I was in a rural area. But it's easy to manipulate an algebraic equation. So to find the resistance, by solving for R, the equation then becomes this: R equals E over I. Or to find the circuit current using Ohm's law, we must divide voltage by resistance, or I equals E over R. Okay, it's just a simple thing to find what you need to deal with. But you know, we've got blueprints and we've got line drawings and we've got a nice little computer screen that'll tell us all of that information. So why do we need to know that? Well, we'll talk about that. So here is an Ohm's law wheel. I took this, and I've got to give credit to Uglies, because this came out of the little Uglies book. And if you don't have an Uglies book, and I'm not promoting Uglies per se, but it's one of the best resources I've found in my career to remind me of the basics of how we work with electricity. So this came out of there, and it's a pretty good equation to look at. So if you know two parts, say the resistance and the voltage, you can find out pretty easy what the flow is. You've just got to change your equation. So let's go into electricity flow. Electricity can only flow in a complete circuit. So if we don't have a complete circuit, all we got is electrical potential. So let's look at an outlet in our house. If you put a voltmeter on that outlet, you're going to find probably somewhere close to 120 volts on that outlet. But that's just electrical potential, because the current cannot flow without a complete circuit. So now you plug in your toaster, you press the little button on the toaster, and now you've got a complete circuit, electrons flow, and all of a sudden you've got toast instead of dry bread. So for it to be a circuit, there's got to be at least two elements. One, a force or a source, and two, a conductor to complete the circuit. So a third element is normally part of a circuit, and that's the load. That's the toaster, toasting your bread. So can we have a complete circuit without a load? What do you think? That electricity's got to do something, doesn't it? If we don't have something for it to do, it's just potential, correct? No matter, even if we have a complete circuit. So it's just potential. So conventional circuit flow. Conventional current flows portray current flow from the positive source to the negative terminal by means of a wire or other current carrying pathway. Pretty simple. That works in both AC and DC. The direction of the current flow in a circuit can be shown in two different ways. One, the flow of electrons, and two, electrons are negatively charged particles that flow from the negative source to the positive terminal by means of a wire or other carrying pathway. Now, does it really matter which way they flow? Yeah. Now that's electricity 202. So we're not going to discuss that. So there's a lot more than what we're going to talk about today. So I've got a demonstration. Actually, I've got 3 demonstrations. So I'm going to walk you through setting up a presentation here today. So I have a homemade device. What it consists of is a cord cap, some number 12 SO, terminal block, a piece of wood, and some number 10 solid core conductor. And if you'll notice that coming out of my cord, I've got a ground, which is signified by green. I've got a hot, which is signified by black, and I've got a neutral, or return, as signified by the white. Now, I've taken the opportunity to take the insulation off the end of the neutral and the hot wire, and I'm going to do a little demonstration about the power of electricity. So I stopped at the grocery store on my way in this morning, but I got some nice tasty, it's just Frank's, I call them hot dogs. some of those nice tasty things. Now, I'm old enough to remember growing up in my household, we had such a thing as called a Presto hot dog cooker. What it was 12 prongs arranged like this, and you put your hot dog between the two of the prongs, and it would cook that hot dog. And they were really good tasting hot dogs. They were very good. Now, I think they took them off the market because there's such a potential for people getting hurt. But essentially, that's what I'm going to do. I'm going to take this hot dog and I'm going to string it on the one, and then I'm going to string it here on the other one. I'm going to set that down there, and I don't want to get that nice tablecloth all greasy. And I am going to apply electricity to that hot dog. So if I do that, what's going to happen? Oh, can you hear that? Can you see that? It's starting to smoke and get hot. It's cooking that hot dog. The terminals are not touching between the hot and the neutral, but I've created a circuit. That hot dog is hot. So it's cooked it from the inside out. And that's what happens when electricity gets underneath our skin and flows, is it cooks our soft tissues. But when electricity enters our body, gets past the resistance of our skin, that's one of the things that happens. And we don't want that to happen, do we? You know, that's a tough thing when electricity gets underneath our skin. So does that mean that anytime we come in contact with the electricity, that's what's going to happen to us? No. How many of you have had the opportunity to get a hold of 120 volts, say in your home, maybe a light socket or something, and you did that 60 cycle dance? Most people have. By the time they get to be adults, we've all seen and felt that 60 cycle dance. So that means that Ohm's law applied, and even though we came in contact with 120 volts at a maximum of 20 amps if you're in your house, it depends on your circuit breaker, we had enough resistance in our body that we didn't get hurt. We just did the dance. So what's that resistance in our body? Well, it's our skin. You know, that's what protects us. But, you know, if you look at the statistics out there, 120 volts kills more people in this country every year than all the other voltage levels combined. So how come you got off with a 60 cycle dance and somebody else died? Or even went to a burn ward? Now there's a lot of factors, but on a nice sweaty hot day like it is here in South Carolina, I can tell you I'm already starting to sweat. I'm having to wipe that sweat off my arm. Would that have an effect to the resistance of my skin? Yeah, it would. Or maybe I've got a cut or something where I've compromised that layer of resistance. Would that allow electricity to get underneath my skin, get into my muscles, get into my soft tissues? Could do. So even that household current, 120 volts, can kill us. But it also cooks a really good hot dog. So safety principle number 1. Takes approximately 50 volts to break the electrical resistance of your skin. Well, we were just talking about 120 volts, right? So if voltage breaks the skin, current can flow and you can be injured. So electricity's effects on the human body, and we've all seen PowerPoints or photographs like this. The minimum current a human can feel is 1 milliamp at 60 cycles. 1 milliamp, you can feel it. But in your house, you've got a minimum of 15 amps, maybe 20 amps. So that dance gets pretty lively, doesn't it? So let go current, in other words, you can let go of it after you contact it, is around 9 milliamps. And current over 10 milliamps can produce a painful to a severe shock. Now, we've all walked away from that 60 cycle dance, oh man, that hurt. And as little as 50 milliamps can affect the electrical system that regulates your heartbeat. Now we're getting serious, right? Yeah. In short, your body is very easily harmed by a small flow of current along the right path. So even our house that we live in has ways and means in it to protect us, and we're going to talk about those. But if something goes wrong, just that house current could kill us. Pretty easy. 3 factors of electrical shock. 1, the amplitude, the extent of current that flows on the surface of the skin or through the body. The greater the current amplitude, the greater the harm or impact if the current is 9 milliamps or more. Okay? That's milliamps. That's thousandths of an amp. And we've got a minimum of 15 amps in our house. Something to think about. The path through the body, hand to elbow, hand to hand, or hand to foot or feet, or over the surface of the skin, usually from sweat or other moisture on the skin. And duration. The time the current passes through the body or the surface of the skin, and the longer the duration of the current flow, the greater harm or impact of shock if the current is over 9 milliamps. And we know that household current is over 9 milliamps. Now, what part of that we take on that particular circuit is up to the way that that circuit is formed. If it's got a lot of resistive loads on it, the available current to us is going to be less. But if there's no loads on it, we could have the full 15 or 20 amps. Now that's kind of sobering to think about. But here later in this presentation, we're going to talk about some protective devices and how they work. So don't lose faith yet. So AC current. Voltage output of DC is different than AC. DC output is steady over time. So DC direct current is steady over time. The voltage remains the same. Generators are the common source of AC, and from here on we're really going to talk about AC because that's in our systems, in our homes, and every place. So AC can be transformed and transmitted over long distance with little power loss, and that's primarily why we use AC current in our systems, because we have little loss of power. AC voltage is represented graphically using a waveform called a sine wave. And the sine wave illustrates the rise and drop in the voltage. And loads in circuits, AC circuits have a resistive, inductive, and capacitive loads. And that's probably electricity 505 or something down the line where we talk about resistive, inductive, and capacitive loads. But it's good stuff to know. Resistive loads are electric heat, light bulbs, ovens, ranges, toasters. The resistive loads and electric energy is changed to heat. In an inductive load, there are motors, transformers, and any device which relies on magnetism to operate. And capacitive loads are any device which has capacitors and synchronous motors. So we have all of those types of loads in our system. So the voltage output of an AC source is not steady. So in one cycle, the voltage rises to peak value and then diminishes to zero, reverses and builds to a negative peak, then diminishes to zero again, and that's the sine wave. We've all been taught this. I'm not telling anybody anything new here, but let's remember this. Alternating current's the most used method of electrical power distribution. We have a generator, we have a resistive load out there, and we have a circuit. Pretty simple. So, on circuits, there are 2 basic types of electrical circuits. There's a series circuit and a parallel circuit. Circuits can also be a combination of a series parallel circuit. So understanding these circuits will help us learn how to calculate basic circuit values when components are connected in series parallel or in series parallel configurations. Again, very basic stuff. In a series circuit, the current flowing through the circuit is the same in each element. So that resistive load does not change. The total resistance of the circuit is the sum of the individual resistors. And as current flows through a resistance, a voltage drop is developed across that resistance. And that's important to realize and understand. So the sum of the voltage drops across each of the circuit elements equals the source voltage. Parallel circuits. Parallel circuits allow 2 or more paths of current to flow. This allows individual components of circuits to open without affecting the rest of the circuit. And in parallel, each component of the circuit is connected across the power supply individually. And voltage is the same across each circuit element. And the current flow through each element is calculated using Ohm's law. Wow, we're back to Ohm's law, aren't we? And we have parallel circuits, we have series circuits in our systems and in our homes and everywhere we look. And the total current flowing in the circuit is the sum of the individual branch circuits. Pretty easy. It's just a mathematical equation. Series parallel circuits, now they're a little bit more complicated. It combines both series and parallel circuits. Calculating the current, voltage, and resistances and power flows, the same rules and procedures as for the series or parallel circuits separately, but you've got to calculate them separately. In a series parallel circuit consisting of several resistances, the key factors are determining the RT, which is the resistance total, and the current total, the IT. Okay, and then we can figure out that circuit. And we've got lots of these in our systems. We're doing a lot of that in our URD systems now. And there's a lot of reasons why we use series parallel circuits in those. Now, we need to talk about phases. So AC is generated at the power plant as three-phase power. Now here's a sine wave that illustrates three phases. So we got A phase, B phase, and C phase. And they're all part of that sine wave. And they're all 120 degrees apart. Now if you know anything about transformers and other devices, you understand this very well. Distribution systems, though, contain single-phase, two-phase, and three-phase lines. Now this is examples of all of those. Now, single-phase and three-phase is pretty common. But in a lot of urban areas, we end up with two-phase lines as well. And some rural areas, I've seen extremely rural areas that we're ending up with those as well. But we got to understand what we're seeing up there, or what we're seeing in the ground. There are two basic types of three-phase connections that will be found on a system. One, there's a delta, and that's the illustration for the delta system. And then there is a Y. Okay, they are very different. So the delta systems. In a typical delta system, there is no neutral wire. This is referred as a closed delta and requires three wires for the connection. In closed delta systems will operate even if one of the phases is out of service. The capacity of the service, however, will be about 57% of its normal rating. So if you get complaints from customers that, well, the lights are on, but we can't get anything done, or something's wrong, it's burning my motors out or something, that should be a clue on how Ohm's law applies and how we fix it. Y systems. A Y system is derived by connecting one of each side of the three windings to a common point. And then the opposite side of the winding is the phase connection, and the common point is called the neutral. So in Y systems, we have a neutral, or a return. And there's some electrical equations for you. Three-phase Y's connected services will not operate if one of the phases is out of service. Okay, need to understand that. So customer load connections. The distribution system is almost exclusively a Y system with the neutral grounded. Okay, that's most systems, but we do see other systems around the country. For a customer, the choice of which connection to use is based on the desired service voltage and the operating characteristics of Y versus a delta system. The selection of voltage level depends on what type of equipment the customer will install, the amount of power the customer will require. So let's just talk about this slide for a minute. If we have a problem and we're out to diagnose the problem and fix the problem, isn't this important? Okay, we can look at it and see how it's wired up. But if a customer's got a problem, maybe we ought to think about these things before we jump to conclusions. So let's talk a little bit about safety, personal protective methods, and personal safety devices. Okay, we're going to talk about grounding and what it does, and bonding, which is your protection, and then we're going to talk about some devices. So I want to preface this part of the discussion into telling you that our electrical system, the safety factors in it are built to save the system. There is nothing out there on the line that you're going to see that is built for personal protection. Now, we do get some basic protections out of the system being built to protect the system. And we've survived out on the line by utilizing those safety factors. But we got to understand that the system is built to protect the system. It's built to serve the customer, but it's built to protect the system, not protect us. So, grounding and bonding. Grounds are installed for the purpose of tripping and enabling overcurrent devices to operate faster when responding to faults. That's what we want it to do. If there's a fault, we want it to open quickly as possible. Now, there's various elements on how quick it will open, and that's electricity 202 or 303 or something. But in 1910, 269 and 4III, now that is a vertical standard for us in our industry. That means we got to do it. It says protective grounds shall have an impedance low enough so that they do not delay the operation of the protective devices in case of accidental energizing of lines or equipment. Now, let's think about that statement. They shall have an impedance low enough. How do we know that they have an impedance low enough? Got a nice little tester with you? Test those grounds, see what the impedance is. What about the connections from those grounds to the system? Could you have a high resistance or a high impedance connection? Would that affect how quickly that system operates? There are rules on protective grounds, what they can be made of, what they've got to do, how you do the connections. Most of us will install grounds without ever looking at those connection points. I see it happen day in and day out. I see it all the time. Yeah, we got a set of grounds most of the time, and I was with a crew last week, got grounds out. They actually got 2 sets of grounds out of a truck. This is on the transmission system. Unrolled them, put them up without looking at them, without doing anything. They just got them out of the truck and installed them. Now, that's a problem. Ohm's law applies there, guys. Bonding, that's different than grounding, is installed in the work area to eliminate potential hazardous differences in potential that could harm the worker. So in 1910, 269 N3, it says the equipotential zone. It says temporary protective grounds shall be placed at such locations and arranged in such a manner that the employer can demonstrate will prevent each employee from being exposed to hazardous differences in the electric potential. Now that's OSHA. It doesn't tell us how we got to do it. It just says we got to do it. We got to establish that equipotential zone. And that's been in place since the 80s. We've known about this. And we still see crews every day who don't do it. And the attitude is, well, I've not gotten killed in doing bracket grounding or whatever method of grounding you're doing, so why should I change? Is OSHA going to come out and write me a ticket? Probably not going to see OSHA until something bad happens. But we ground to trip the system. We bond to protect us as workers. Grounding alone will not protect you. We know that. So safety principle number 2. Current flows in every available path inversely proportional to the resistance in the path. Now, when I started in this industry, we used bracket grounding. Okay? Fault comes here, hits those grounds, goes to ground, I'm safe because I'm on this side of the ground. It comes from this side, hits those grounds, opens the system, I'm protected, right? That was the theory or the way that we thought about things. We were wrong because current flows in every available path inversely proportional to the resistance in the path. So if you got high resistance grounds and you don't have any bonding, are you going to trip the circuit? Now, cycles matter. Now, Electricity in the U.S. travels at 60 cycles a second, right? Those cycles matter. The difference between 3 cycles and 30 cycles could mean the difference between life and death for you. And if you've got a high resistance grounds on, it's not going to trip the system as fast, and you're putting your life at risk. Plain and simple. Safety principle number 3. If you insert a resistance in a current-carrying grounded conductor, a voltage rise will appear. The voltage will be proportional to the resistance in the path. So how does Ohm's law apply to that? Think about that. Do the math. See what's going to happen to you. A truth. Every ohm of resistance you build into your protective grounding system raises the voltage across your body in an instant. If we're not inspecting the grounds, if we're not testing our grounds, if we're not making sure the connections are free of corrosion or got dropped in the mud or whatever, if we're not wire brushing them, and if we're not brushing and making sure the conductor that we're hooking them to is okay, and if we don't tighten those grounds down tight, all of those build resistance into that grounding system. All of those do. We got to pay attention to that because we want that circuit to trip out as quickly as possible. Now, a lot of systems are set to trip at 3 to 6 cycles. We, by our own laziness, are increasing our danger. If it's set to trip out 3 to 6 cycles, okay, we're good. But if we build resistance into that grounding system, it may not trip out in 3 to 6 cycles. If the engineer has set those cycles up because of nuisance tripping to, say, 30 cycles, that's 10 times 3 cycles. We're 10 times more likely to get hurt than we are at 3 cycles. And now we got more resistance into those grounds because we're not paying attention to how we put them on, what the conditions are, what the conditions of the wire we're putting them to or the bus work. We don't care. We're making sure that we're doing what we can to trip out the system, but we're really not thinking about that. Now, a lot of systems are built with pole grounds. Now, when you replace a pole, you put a ground on it, and a lot of systems have a ground on every pole or every 2 or 3 poles or whatever. And we're thinking, okay, something goes wrong, it's going to come out to that grounded wire, it's going to go to ground, we're going to be good, right? You know that there's a standard that says that those grounds have got to be measured at 25 milliamps. How many of you ever done that in your system? Have you tested that ground to make sure that it is a low resistance pathway? Or is the very thing that you're doing by throwing the ground rod in the pole hole with you and tamping it in, which is a common practice, or using a butt ground, or whatever, we just assume that it's going to protect us. We assume it's going to protect the system. But are we building our system to make it more hazardous for us as workers? We need to think about things like that. So if we control the voltage, the current doesn't matter. Okay, pretty simple concept. So overhead grounding and bonding. If the pole and the wire are at the equal potential, no current flows across the worker. So here's what we're supposed to be doing now. We're creating a work zone. Now, we're all on a pole putting up that little pole bracket below us, or below us when we're in a bucket. I hope we're all doing it. Are we making sure that it is a good pathway? Are we making sure that each of our connections are the least resistance or least impedance that we can obtain in that? Are we making sure that our body, no matter what we touch or come in contact with, is the same electrical potential? Now, I'm a skeptic. I'm an old farmer rancher. I've been one of those people in my whole career that I'm going to draw out a circuit, or I'm going to draw out the system, and I'm going to go through all the what-ifs before I go to work. Because I figured early on, in here, in this line of work, that if I did not take care of myself, nobody else cared enough about me to do it. Because all as I got is, get up there, Turner, and get it done. Now, that was a kind name. That was not the name I was called for a couple of years. It was a lot different than that, but that's all right. But, folks, if we don't take care of our personal safety, who will? If we rely on the system to protect us, it was built to protect the system, not us. If we rely on those grounds that we're putting up to protect us, it's only going to trip the system when. If we're doing personal protective grounding, but we're not looking at the system that we're putting up that's going to protect us if a fault occurs, why are we putting them up? If your life don't mean that much to you that you can't take a minute or two to look at that grounding equipment and that bonding equipment to make sure that it has good connections, that there's no high resistance issues in it. If you can't wire brush the connector and the wire or the bus work that you're putting it to before you put it on to make sure you've got a good connection, if you're not putting it on there just as tight as you can, you're leaving yourself open, folks. Hey, it's my turn today. I'm going to get electrocuted, or I'm going to come in contact and get a flash burn. That's what you're saying. My turn today. I'll take one for the team. I don't understand. I don't understand why we're not taking care of things. So, how do you isolate a URD cable? Ground the cable using conventional means with the bushings, lead connected to the system, neutral in the enclosure. After verifying the cable is dead, connect the bushings lead from the ring bus to the enclosure and connect it to the cable's concentric neutral. Isolate the concentric from a system neutral by disconnecting it. If the bushing ground and concentric is isolated from all other potentials in a blanket, take all necessary precautions when disconnecting the concentric regarding the system neutral current. Now, on the overhead, we were taught that we never get in between two ends of a neutral, right? Yeah, basic thing taught very early on in my career. But why are we willing to do that in the underground system when we're working on it? Getting between two ends of a neutral. We see it all the time. So if the phase is effectively isolated, meeting the requirements of OSHA, can be worked safely without grounds or bonding. Folks, just got to take these extra steps. I know it takes a little bit of time. And I've been called lots of names. Been called a sissy, been called an idiot, I've been called a lot of names that I don't want to mention. But I care about my safety. I care about your safety. So as I'm preparing out on the job to make sure that I have all of the conditions present that will protect me, now I rely on my behavior after that to protect me, but I'm also protecting you as my coworkers. Why aren't we doing it? I don't understand. 4 recommendations on how to make grounding for personal protection work. 1, understand the sources of current flow. 2, understand the paths that are available. Sometimes we got to think about that. Number 3, understand how to bond in or how to electrically isolate or insulate yourself, and understand the limitations of the methods chosen. Very simple 4 rules on grounding and bonding. So I'm going to switch up a little bit here. And I'm going to go into overcurrent protection, or fuses in this case. The overcurrent devices commonly used to protect branch circuits in dwellings are fuses and circuit breakers. Okay. And we still see some of these type S fuses, or the penny that we put in them because we can't find one to replace it when it blows. That doesn't do us or the installation any good. On the power system, control fuses and power fuses are used to detect problems and operate to prevent equipment damage. Fuse blows, right? System's de-energized, right? According to the rule book, it's got to be both electrically open and mechanically open. Does a fuse do that for us? Depends. In dwellings, we normally use thermomagnetic circuit breakers. This is in your house or your place of business. A continuous overload, a bimetallic element in such a breaker moves until it unlatches the inner tripping mechanism of the breaker and the breaker opens. And most circuit breakers are ambient temperature compensated. They're made to be inside your dwelling. And so they're put together in such a manner that they thrive on the temperatures in your dwelling. And it's a good practice to turn the breaker on and off periodically to exercise its moving parts. Now, fire departments and investigators find a lot of times in house fires or dwelling fires that the circuit breakers did not operate. And that's because they haven't been operated for a long time and they won't operate. Now, I don't know how many of you ever, twice in a while, go to your circuit breakers in your house and switch them all on and off to operate them. Not many of us do, because now we got to go back and we got to reset the clocks and we got to reset all the timers, and we got lots of other stuff to do too, so we don't want to do that. Or the power goes out, company failed to deliver power to us, it comes back on and we're good. Well, how do you know there wasn't a power surge or something that could have fried a protective device in your home? How do you know that? Unless you operate it to make sure. But it is a device, again, that protects the system. Overcurrent devices are there to protect the system, not you. They're built to protect the system, not you. They're built to protect your house or your electrical system or whatever. There is nothing in these devices thus far that protects you as a person. Until we get to this device. GFCIs, a ground fault circuit interrupter, is different than a GFI in our system. They are two different animals. A GFCI we will find in our dwellings. It is a device designed to protect us as people. It is one of only two devices in our installations that will protect us. So I've got a demonstration here, so bear with me a little bit while I put this little demonstration together. I have my bathtub that I travel with. It's a container that's going to hold some water. Now, I stopped at the grocery store this morning, and just so that I'm not playing tricks with you guys, I've left it in its vessel. It's called drinking water. It's purified with minerals added for flavor. Drinking water. Or water that will come out of your tap and into your bathtub. We're going to pour it into our tub. Okay, we don't want to overfill the tub. Now, one of the things that we're taught is these devices that are in the bathroom. Now, I don't need one of those devices anymore, but I carry one anyway. That if we drop that in that tub of water, it could really do some damage to us, couldn't it? So I've modified this a little bit, but this came, instead of this cord cap on it, it came with this cord cap. And it is a GFCI. So it's got a test button on it and a reset button, but I cut it off. But also it came with a tag. It says, keep away from water, danger. Always unplug it after use. Do not place or store where dryer can fall or be pulled into the tub, toilet, or sink. Do not use while bathing. Do not use near or place in water. If dryer falls into the water, unplug immediately. Do not reach into the water. And just to illustrate that, got a nice little diagram for us who can't read. It says that we don't want to put that in water. I have also made up a little cord cap type situation that I'm going to use. So I'm going to plug this into my source of electricity. Now, This is a GFCI. It's an inline GFCI. So if I test it, it says that it's good, right? Now, I can also test it with one of these little doohickeys that we can get at any hardware store. And if I plug that into it, all the lights are on, and if they're on the way that they should be, it says that it is correct wiring. Because I've got this light on, and that light is off. You read the legend there, it says everything's correct in that. So everything should operate correctly with my GFCI and my hair dryer. Oh, man, listen to that. That operates so good. So what's going to happen if I drop this into that tub of water? Am I going to get electrocuted? Well, let's see. All I got's a motorboat. Why didn't it trip out? Got a working GFCI. What the heck's wrong here? Got a 2-wire system. Well, what'll happen if I put this grounded wire? Fixes the system, right? Tripped it out. Why didn't it trip out before that? So what causes a GFCI to trip? In a properly functioning circuit, the current flow through the hot wire is equal to the current returning on the neutral wire. Okay, that's in a properly functioning circuit. The GFCI continuously monitors the current flow in the circuit. If it detects a difference, typically 5 milliamps or more, it assumes that some circuit is leaking to the ground. Upon detecting an imbalance, the GFCI trips. The GFCI trips and the circuit cuts off the power supply to prevent harm. So GFCIs work if there is an imbalance between the hot and the neutral. Now, on a 2-wire system, like your hairdryer there, what would cause an imbalance? If you have a 2-wire system in an old home, will your GFCI still operate? Maybe you better go to school and get those answers, because I'm not going to give them to you today. We think of GFCIs as nuisances, or nuisance tripping all the time. And we blame that on overcurrent. But GFCIs do not see overcurrent. They see an imbalance. So they will not operate on an overcurrent. But how come it always trips out in your house? It's because we cause an imbalance in the circuit by too many things plugged into the circuit, and then you hit your toaster, which is immediate draw on amps, and now we have a voltage drop condition, and it trips out. Or we're out on the job site, and according to OSHA, everything that we use out there has got to be GFCI protected. So we string out a 100-foot number 14, number 16 electrical cord and plug a lot of devices into it and wonder why the GFCI trips out. Well, it trips out because there's an imbalance. It means you're drawing so much on the one leg, on the hot leg, that the neutral leg momentarily don't see it. It sees it as an imbalance, and it will pop the GFCI. They do not trip out on overcurrent. That's a different device. They only trip out when there's an imbalance between the hot and the neutral. And we had to create that on this hairdryer by having this green wire hooked up to the ground in our system and created an imbalance on the hot and the neutral in order for that to operate. they're important to have, folks. It's one of only 2 devices in all of the electrical system that is made exclusively for us as humans, to protect us. So don't take them out of your circuits. Put them in there. If it's tripping all the time, you've got a circuit that's not wired properly for the loads that you're trying to put on it. Plain and simple. If it's tripping out on a job site because you got 100 feet of number 16 extension cord, change it up. Spend a little money, go back and get number 12 or number 10, and you won't have that nuisance tripping anymore. So let's talk about voltage drop a minute in relationship. Low voltage can cause lights to dim, motors to run hot, electric heaters to reduce their rated heat output, and appliances to operate improperly. So low voltage in a home can be caused by a wire that's too small for the load being served. Poor connections at the terminals, you got a high resistive connection. Conductors operating at high temperatures. Hot conductors will have higher resistance than when operating at lower temperatures. So a conductor's resistance depends on a lot of things: the size, the material type, and the temperature. Now, in today's world, where a lot of our conductors are made out of aluminum, we know that they have more resistance. So we got to take that into account when we build our systems or our circuits, if we're using aluminum wire. Some of us old school people, I'll pay more for the copper. So that's just me, but I understand things well enough that if I wire a house like I'm getting ready to do, here I'm building a house currently, I've already bought number 10 copper wire for the whole house. Now it cost me about double, or maybe a little more than double, than if I'd have bought number 14, but it's worth it to me, because I don't want a problem down the road because of voltage drop issues. Arc fault circuit interrupter, what the heck is that? Well, it's about a $100 device. An AFCI is designed to detect a unique electrical signature of arcing conditions, which can occur due to damaged wires, loose connections, or deteriorated insulation. AFCIs can distinguish between harmless arcs, such as those from a switch or a plug operation, and hazardous arcs that can lead to fires. When a hazardous arc is detected, the AFCI quickly shuts off the circuit, stopping the flow of electricity and preventing potential fires. Now, the electrical code says that those have got to be in rooms or areas where you sleep. And the theory behind it is if somebody's sheetrocking your house or putting wallboard on it or whatever, and they screw a screw or pound a nail into a wire, and it doesn't connect, it doesn't cut it all the way, but it contacts the wire, over time that electrical arc will get bad enough that it will eventually start a fire. They have it in your areas of your home where you sleep so that you have a chance to cut that off before you see the smell the smoke or see the fire. But it is also a device there to protect us. Here's what we need to remember. Electrical incidents can be serious and even fatal. Even the most trained and experienced workers make mistakes. If we know, remember, and practice basic electrical principles, incidents can be prevented. Electrical injuries, even if not fatal, are devastating. Anyone who's visited a burn ward knows. Now, I would suggest that if you're in the electrical field, take some time and go visit your nearest burn center. Shake hands. It's an experience you'll never forget, ever. All the electrical incidents can be prevented. It's not that hard. Knowledge of and implementation of basic electrical principles is our responsibility, and we deserve to be held accountable because we're professionals. So I'm going to do something that I'm not going to recommend that you do. So only trained professionals need to be doing this. I'm going to get this demonstration out again. And on the way here this morning, I was a little hungry, so I stopped by and I picked up a jar of kosher pickles. And we're going to take one of these pickles for our demonstration. Makes me hungry. Now we're going to do the same thing with it that we did to the hot dog. So we are going to plug this in, and we're going to see what happens to this pickle once it's exposed to current. We've checked our circuit, made sure everything's okay. So this should be working here. It is. I can hear it. I can see the smoke. And you know, see that arc in there? That arc is contained into that pickle right now. But that's what happens to electricity when it enters your body. It lights you up, folks. It will literally light your system up, just like it does that pickle. We're at the end of our presentation, folks. I'm here because I believe in what Beer Meters is doing. It is providing a platform for all of us to learn from. And when I say all of us, I mean me as well. I don't know everything. And I'm human, I make mistakes. What we got to understand though, we might work our whole career, never have any electrical contact, never get burned. But each and every day, we've got to operate on the text that it could happen to us today. So remember our basic electrical principles. Remember what we need to do to stay safe. Remember that the system's built to protect itself, not us. Whether you're in your home or whether you're out on the line. It's been my pleasure and my honor to be here. If you have questions or if I can help in any way, my contact information's here on this slide. Thank you. We'll see you next time.